we are working on, so I want to say more on three-level systems. We started seeing interesting effects that happen in the three-level system. Specifically, we discussed in the end of the last meeting, and I'll remind you a little bit more. We discussed Theorem. I'll talk a little bit about this ability to do a very robust adiabatic transfer of population between states, which is even much more robust than the adiabatic rapid passage that we discussed in the two-level system. So this is, we mentioned stirrup. I'll briefly review that soon. And then we'll say a little bit more about these things. There will be EIT, electromagnetically induced transparency, situations where in a three-level system you could have a transparency window on the atomic absorption. So you have an absorbing medium, and you force in the middle of this absorption line, meaning you're on the absorption line. Suddenly you open there a window of transparency, that the medium becomes transparent. And it has some interesting effects that are related to this. So this is called electromagnetically induced transparency. And I'm lazy, so I'm not writing the entire word. And it goes with effects of slow light, also it has to do with fast light, but slow light meaning situations where the group velocity, I don't know, the velocity of light, some kind of velocity of light inside a medium is slowed down to 17 meters per second. You can almost run this fast. Well, you can. I'm not sure about myself, but and so all kinds of tricks that have to do. It has also another name, and that is shallow towns splitting. The point is that I never remember how to spell shallow. I think it's like this, but I'm not sure. If somebody can check, shallow is a person. Towns, I know. All of those are related effects, and we'll say something about those things so that you'll know them. But the more important thing that we will be spending most of our time on is coherence theory. We'll talk about the coherence of light. And in this case, it's going to be classical. But why? Because it is necessary to know classical coherence if you want to discuss quantum coherence. And quantum coherence will come in pretty fast after that. So this is our last part before we quantize the electromagnetic field itself. So before we go to look at the quantum field. Oh, and there's the and oh yeah, but and classical yeah. classical coherence. And in this part, we'll be discussing first order coherence, and if there's first order coherence, then there's probably also second order coherence. Actually, there's not just one, there's many of them. So this has to do with the field. This one, people usually say that it has to do with the intensity, but that's not true. That's one of the possibilities of having a second order coherence, which relates to the intensity, the properties of the intensities, but that's not the only thing that could be of second order. And I'll show you others that are very important as well. The last thing that we'll do in relating to the coherence theory will be a semi-classical theory of photodetection. Why am I going to say something? Now, these things, hopefully we'll finish all of them today. Maybe not. Maybe some of this will be left for next time. But I want to say something about why are we wasting this time? Well, primarily in order to root out misconceptions that you definitely have. One of the misconceptions that I'm sure all of you have is that a photon is a click. If you have a click on a photodetector, that's a photon. Well, we're going to talk about what happens when you have a completely classical wave, classical light, hitting a detector, but this detector emits electrons, and derive the statistics of photodetection events under this assumption. Light is completely classical. The detector has some probability of generating an electron once light hits. And we can discuss what will it tell us? What will be the statistics of the detection events? What will be the noise? What will be the properties of this photodetector that is looking at classical light? And you will see that it generates really a lot of the properties that we see with photodetection. So the fact that you have clicks on a detector, that by itself has nothing quantum in it, at least not of the light. The detector has single electrons, and you can call this quantum. The matter is quantized. Surprise, surprise. Electrons are discrete. But once you understand this, or you accept this fact as not being too surprising, the fact that you have a click is the fact that you generated a single electron. And you know, I can take this lamp, which is rather intense and definitely classical in most aspects of its behavior, and I can take a detector. And you know, to make a detector very good requires a good experimentalist. But to make a detector bad, that's easy. Everybody can do that. So I'll take a detector that is so bad that even in this light it will generate single events every once in a while. And then you'll see that you have, well, you'll have what? Single photons? Well, no. Well, that doesn't tell you. You have single electrons. You have a really bad detector and it generates single electrons. But does this tell me anything about the nature of the light, and is the light quantum? Likely not. Okay, so this is why we want to spend some time about this, because it will show us things like shot noise. People think about shot noise as being the classical limit. In some sense, it's true. But, okay. So, that's the plan for today. Let's start. Where is that's what does the Luach. Ooh. Okay. So, let me remind you some of the things about the three-level system that we were discussing. So we wrote what we did last time. I'll remind you very quickly about stirrup, but what we did was discuss the three-level Hamiltonian. So the state is, I don't know, some vector A1, A2, A3. They relate to some three levels that we can generically call 1, 2, and 3. I'm drawing a lambda system, but it doesn't have to be a lambda system. Nobody said where number 3, state number 3 is. And I'll say in a moment something about. But then we would have what we call the one photon detuning and the two photon detuning delta 2. And this was omega 1 and this was omega 2. It has, or atomic frequency. Small omegas are related to frequencies, optical frequencies, where large omegas relate to Rabi frequencies, or basically to field intensities. And so we have a state like this, and we have the rotating wave Hamiltonian after the rotating wave approximation, which looks like, okay, so we would have here 0, delta 1, delta 2, omega 1 star. I think here we have omega 2 star, omega 2, but the question of which is a star and which is the only thing that would make a difference between, for example, this level and the ladder level, where we have, say, this detuning delta 1 and this detuning delta 2, the only difference between this lambda system to a ladder system is just the fact that these two flip their position. Why? Because in this case, in order to go up, to reach from 1 to 3, I need to absorb twice. So that means, if you remember, one of the, what happened? Well, the field, of course, contains both the amplitude and the complex amplitude are there. So the field itself contains always, that's a reminder, this A e to the I omega t plus A star e to the minus I omega t. That's always there. And these omega and omega star are nothing but the fact that we take this and we multiply it by the dipole and we divide by h bar. So these guys only reflect these, and with rotating wave approximation you keep one of them. Now when you go up and up again, you'll keep the positive frequency components twice. Whereas when you go up and down, then on the way down you'll need the negative frequency component. And that's why the only difference of one three-level system to another is just the question of whether you put it's just the convention of which one is the complex conjugate and which one is not. So that's why I say the fact that we're doing this right now and looking at the three-level system that looks like this, there's nothing special about it. You're really analyzing any three-level system you could think of. So and as we said last time, we can write this I psi dot equals h, of course rotating wave times psi. And as we mentioned, this psi now is in the rotating wave, and in the rotating wave those are the energies. And this, we can solve. So this becomes an equation that says I A1 dot A2 dot A3 dot equals this matrix that we had there. I'm not going to write it, times A1, A2, A3, no dots. And what we did last time was to solve this. How did we solve this? Well, first of all, I must say that we didn't exactly solve it. That's the equation. That is indeed the equation. But we did some adiabatic approximation. What did we do? We diagonalized the matrix. We diagonalized the Hamiltonian and found its eigen energies and eigen vectors. So what we did last time was to take a specific case, which is what we call two-photon resonance, and it sounds like something that would be interesting. Meaning that the first laser can be off from the second state, from the intermediate state, but both lasers together are on resonance with the target state. So under the assumption of two-photon resonance, now notice the name two-photon here is misleading. Nothing photonic in what we're doing. Light is classical completely. But on two-photon resonance, where delta 2 equals 0, we found the eigenvectors. Actually, we can do this also when delta is non-zero. It's just that when delta 2 is 0, you have a special property. Okay? So we found that there are three eigenstates. Lambda 0, which is 0, and that's the point. If you're on two-photon resonance, there is always an eigenvalue which is 0, and this is robust. And there's this lambda plus minus, those eigen values. Where are they? I had them once. Let's have them again. Where'd you go? What? Plus minus half square root omega 1 absolute value squared plus omega 2 absolute value squared. So those are the two. And we had the two vectors, and we had this V0, which looked like omega 2 star omega 1 0 times some normalization factor, which I don't care. Of course, you need to normalize this. And we had those V plus minus, which looked like they had something, yeah, that the main point was that there was, you can write them up and you can calculate them yourself. It's easy, but eventually, yeah, let me, where was it? Yeah, let's call it something, I don't know. A, and here there was plus or minus 1, and here there was a B, and of course they depend on everything else. These are complex numbers. I don't want to go into that, because most of what we want to look at has to do with this 0 eigenvalue. Now, so this is unique. It is called the dark state. And this is its name for a reason. It seems to not interact with the field. It's not affected by the field. It doesn't care if the field is there or not. Its eigenvalue is always 0. And it seems to not allow transfer of population into the excited state. There's nothing that goes into the excited state. And then what we did last time was to discuss implications of this by saying, let's think about stirrup, meaning let's think about a case where I want to say a little bit more about those. Stirrup is to say, look, I'll show you how. I'll take all the population from state 1 to state 3 without ever being in state 2. So now mathematically it's obvious. Let's do the following. My population is initially in state 1. So my initial state, V, psi at t equals 0 is 1. It's just this, which is this 1, 0, 0. But this can be the dark state when? This can be the dark state when omega 2 is large and omega 1 is very small or practically nothing. Now, that actually makes sense. So this can be, this is the dark state for the case of omega 2 much, much larger than omega 1. You can take absolute value, but it doesn't matter. Now, and eventually, at the end, I want to be at state 3. Now this state 3 is 0, 0, 0, 1. But this is also the same V0, but now this is V0 for the case where omega 1 is much, much larger than omega 2.
I didn't understand why we need those.
What?
Why do we need those rules in order to happen?
Well, right now I'm just identifying something mathematically. The point is that I want to adiabatically transfer from this to that. So now look, so now we just identified the two end situations. Now this is the intensity and this is time. So this is omega 2. There are many things that seem to be counterintuitive in what I'm drawing. Oh, come on, open up. Thank you. Those things are too thick, inconvenient. And this one is omega 1. Now actually everything happens between those 2 points in time. Now let's think about, and now I draw at the same time population. So that would be population, but I'm breaking it into states. So initially, we start with a situation where, so this is, that one is, let's say, T1, this is T2, or T initial and final. Now, until this point, all population, this will be A1 absolute value squared. Everything is in state 1. This is what we start from. And state 2 is here. There's nothing in state 2. Now, what we do, okay, so that was the original state. All population was in state 1. And if the intensity of omega 2 was large and omega 1 was small, then this was also the dark state at that time. And it's a trivial dark state. It's not really surprising that if you have a very strong laser here, then this state is dark, because there's no light interacting with it, so it doesn't care. And if the atoms are sitting here, then they'll stay. If they're here, they'll be running around, rabbi-flopping, doing all kinds of things. But they're not there, they're here. So yes, this state is dark when there's no laser interacting with it. And this state becomes dark in the end, because then there's no laser interacting with it. So in the end, this one, the dark state is this. So this is where we are at the end. And the population in A1 becomes 0. And what happens in between? Well, assuming now that this is adiabatic, that the transfer is adiabatic, that we slowly that this transition, change of intensities, is slow. But by the way, I don't care about the details. They can be anything as long as this one slowly goes down and this one slowly goes up. It can be linear, it can be Gaussian, it can be whatever you want. Apparently, I don't care. As long as it is sufficiently slow and adiabatic, what will happen is that we stick to the dark state.
Why it needs to be slow? Why we need it to be in a adiabatic constant?
Well, it's the same. We'll understand that in a moment from a mathematical point of view. But let's put it like this. What are we doing? We're changing the Hamiltonian. When we change the intensity of the lasers, we are changing the Hamiltonian. Now, you know that if the Hamiltonian suddenly changes, then the state doesn't change. If you're in a sudden case, if you had a potential well, and it suddenly became twice as wide, and this is an exercise that you all solved a million times, well, you know then that the state doesn't change, and then you have new eigenstates of the new Hamiltonian, and then you'll have excitations, and you'll see that you will have a probability of ending up in an excited state, even though originally you were in the ground state, because the ground state is no longer the ground state. It's now a superposition of new states. But in this case, we're slowly changing the Hamiltonian. And then if you're in the ground state of that Hamiltonian, you'll stay in the ground state of that Hamiltonian. And then indeed, what will happen is that something will do, I don't know, this. And since you are in the ground state of that Hamiltonian, and that ground state of that Hamiltonian does not include anything of the excited state, then there will be no population in the excited state. In reality, if you try to see, is there any population in the excited state, then you'll see, this is not 2, this is 3. This is 2. It is nearly 0. If you ask yourself how much probability is there to be in the excited state, then the answer is nearly none. And I'm sorry, this is not 2, this is 3. Now let's say something about what is adiabatic. Okay? So what do we mean by the adiabatic approximation? What defines slow enough? Actually, we can stay here because this can go. So we're doing so here we have an adiabatic transition of the dark state. So V0, the state V0 is transitioning from 1 to 3. So we have some approximation. So what is the adiabatic approximation here? So where is the approximation that we did? What did we throw away? What does it mean to be sufficiently slow? So if we think for a moment, what did we say? We said that, look, we look at the state as a superposition of the eigenvectors. So if I say what is the state at time t, well, that is, of course, it has some a0 of t times v0. But now let's be honest. This vector is also time dependent. Well, it depends on the Hamiltonian, and the Hamiltonian changes in time. So this, if I just, mathematically, this v0 at time t is the eigenvector of the Hamiltonian at time t. And then there's, so I won't keep the of t because it will annoy me, but everything here is a function of time, of course. And a plus v plus and a minus v minus. And now, what do we do? We have, so now we write this. We write I psi dot equals what? Equals the h. That's always true. H psi. This part is always there, of course. But now, let's look into the first part. What is psi dot? So I, this is of course true, but then we look into here. Well, this contains, when I come to take a derivative of this, it has something that is convenient. That is the derivative of the coefficients. But those vectors are also times dependent. So there is a derivative also of the vectors themselves. So we have here a0 dot times v0 plus a0 times v0 dot. And of course, there is the same for all the others. Now this equals what? This equals h operating on a0 v0 plus a plus v plus plus, let's try to write it nicer. Now, when we open, this side is easy because those are eigenvectors of this Hamiltonian at any time. So the right side is simple. I can now do what I can do on the board, and you can do on your tablets later, which is just to take this out and write here just the eigenvectors. So there will be a0 lambda 0 v0 plus a plus lambda plus v plus plus a minus lambda minus v minus. Now when we look at this and we say, aha, okay, what we wanted to have is to say, look, this, we want to look at this and to say, this here is a dot v0, and here this is the only component with v0, so I want to write a dot equals a0 lambda 0. That's what I want to write. But this would be in this case not exact. This would be exact only if we can throw out this guy and all the other dot guys. So let's think for a moment what would happen if we don't throw them away. So that means that what we need is we need the states, the eigenvectors to change sufficiently slow. And let's see, so let's write the true equation for A0, for example. What do I need to do? I need to multiply, to, do a bracket with what? With V0. Right? If I bracket with V0, then this will dig out this guy. The others would fall out. From here, it will dig out only this guy. And I'll stay, so I'll have, so if we multiply, we close with V0 from here. And what we'll get is indeed A0 dot. But then there will be some additional vectors here. And then here will be plus A0 times V0 dot plus A plus times V0 V plus dot plus. Let's write everything here. Plus A minus V0 V minus dot. So those would be on this side, and they would be equal to what? To A0 lambda 0. Now, these guys I want to throw away. So if I ask myself, what is indeed A? So what we want is then A0 dot. That equals A0 lambda 0 minus all these guys. And then look, assuming that those coefficients, they are going to be of the order of 1. Okay, of course, maybe in the initial case situation, one of them is 1 and all the others are 0. But during during the entire time where things are interesting, they are of the order of 1 or half or a third. But the coefficients are of the order of 1. And then the question is, tell me what is the relation between the eigenvalues, or more importantly, the energy differences, the eigenvalue difference, to this. So what you need is, what we want to do now is, of course, to throw these guys. You want to say, look, we change sufficiently slow, so this time derivative of the state is, it's 0. I don't care. So what we need, so the adiabatic condition is lambda 0. And of course, this was just for lambda 0, but the same goes for lambda plus and minus, is much larger. Then all the products of the form, say Vi Vj dot, and absolute value squared. Now, and as you know, we can always define energies up to a constant. So to say that this is what's important is a little bit misleading. What we care about is the differences. The energy differences how much of a gap is there in the Hamiltonian, which is now, yeah, well, I removed it, but where are they? If there's a question, then I'll answer soon. So look, those are the energies of that Hamiltonian. Those are the eigenvalues of this Hamiltonian. And for example, if all the fields are 0, then all eigenvalues are 0. And then it wouldn't help to do anything of what we just said. If the fields are weak, then we will have to move very, very slow. Why? Because those eigenstates, so what we actually care about, so let me correct this. So what we want here is lambda I minus lambda j, the eigenvalues. So yeah, any energy difference. So if okay, that means that when if those fields are strong, then you can do things rather fast and it would still be adiabatic if the intensity is high enough. Because the splitting between the states is large. So as long as by the way, there can be cases when you're lucky, you're extremely lucky, and that is when this derivative is orthogonal to that vector. And then this derivative can be as large as you want, but as long as it's orthogonal, then the product is 0. But so that tells us where the adiabatic condition comes from. So now there was a beep. Does this mean that there was a question? Yossi Ben Zion wants to join us. We have the master coming in. Should we let him? Yossi, מה אתה רוצה?
לראות איך זה נראה.
אסון, תראה, איזה בלגן.
לא, התוכן, אני מודה, הוא פחות חשוב לי. אבל אם כבר, אתה יודע, אני בדרך כלל נכנס כדמות שקטה שאף אחד לא רואה אותה, אבל אם כבר מצקת אותי, חברים מהבית, אתם שמים לב לשיפור שהכתב הרבה יותר חד, אבל אבי טיפה יותר חשוך?
כן, שמתי לב.
יש בזה יתרון גדול כי הרבה יותר קל לקרוא מהלוח. מה דעתכם על זה?
זה הרבה יותר טוב מפעם קודמת.
כלומר, אתם לא רוצים לראות אותי. בסדר, אני אעמוד בחוץ.
פחות חשוב שהמרצה לא נראה הכי טוב, אבל העיקר זה שהלוח מאוד חד. נכון, אתם שמים לב שהלוח ממש חד, הכתיבה ממש ברורה.
כן, חשוב זה התוכן, לא הכלי.
הבנתי, אני בכל מקרה אנסה קצת להבהיר את האבי, למרות שבעידן הפוליטיקלי קורקט זה דווקא יכול להיות רעיון לא רע שיהיה לנו אחד מהסוג הזה במחלקה, אבל אני אכנס לחדר ואני אבהיר אותו.
אתה רוצה להבעיר אותי?
כן, אני אעשה את זה בלי להפריע. פשוט יתעלמו ממני, אני אשנה איזושהי הגדרה קטנה והוא יהיה טיפה יותר בהיר.
אוקיי.
אבל אבי זה נראה מעולה.
So I think then, okay, so you understand why, what's adiabatic and why is that the adiabatic condition. Let's say a few things about the other things that could relate to this existence of the dark state. And so not only stirrup, and then we'll finish our discussion of three-level system, take a break, and move on to coherence theory. Oops. Yossi, you said before that you see better on the board, And of course, this is a new marker. Last week we had a bad marker, now we have a good one.
You used the regular one?
No, I didn't. The one that we had here was just used, so it was bad. But, so if you want to do an experiment, it must be controlled where all parameters are the same. Okay, so I want to say something about EIT. I'll first say something about what we call the shallow towns splitting. If you have to.
אנשים בבית, מה דעתכם עכשיו?
I don't care, you don't have to see me.
כאילו, הוא הרבה יותר בהיר, נכון? אני לא שומע אותך מיכאל טוב.
הוא אמר שהיה קודם יותר טוב.
קודם היה יותר חד קצת, נכון?
כן, בדיוק.
אבל עכשיו הרבה יותר בהיר.
כן, עכשיו רואים את הרבה יותר טוב.
השאלה אם...
זה בסדר, אני לא פולני, אני לא נעלב.
טוב, תמשיך ללמד, אני טיפה אשחק בהגדרות.
טוב. Okay, so let's first talk about the shallow town splitting, and I'll just, to make things easier for me, I'll write shallow towns splitting. So when we talk about the shallow town splitting, it has to do with the following. Well, suppose now that this, okay, so we have those two lasers, and we have the following. So this laser, so this one, omega 2, it is much, much larger than omega 1. So an omega 1 is sufficiently weak. So this laser, and this one is strong and it's on resonance. So I want to explain the following. So we have this state 1 and 3 and 2. And this is omega 1 is weak. And even more so, I want to change the definition of the resonances a bit, meaning that this guy is going to be exactly on resonance, this laser, and the first laser may have some detuning. So this is a different definition than we had before. Right now, we can have also two photon detuning. So this laser is weak, and it is. But now, let's see. First of all, so something would happen. As I told you before, well, we can analyze this system, and we can find the eigenstates and eigen values, even in that case as well. We'll find that when we have, okay, first of all, when do we have two photon resonance exactly? When we have two photon resonance is when this laser also hits the excited state. So the two photon resonance condition, when the total transition is completely on resonance, is when both lasers are on resonance, because this laser is always on the transition, just sits there. So hitting a dark state, which is truly dark, happens only in the surprising situation when this frequency is exactly on resonance. So when delta 1 equals 0, that's the two photon resonance. And that's when we have a dark state. Now, what is this dark state? I just told you, look, omega 1 is weak, omega 2 is large. So this dark state is state 1. It was state 1, and it stays state 1. So the dark state is state 1, which means that it doesn't interact with the field, or there will be no absorption. We will not. So now the surprising thing, is there a question from home? Or somebody speaking? No. So that means that if we look at the, now I try to ask myself, what is the probability of finding population in state number 2 as a function of the frequency of this delta 1, so of the frequency of this laser? What do we expect normally to happen? Well,
but before we assumed only omega 2 is 0. We didn't speak about delta 1. I mean delta 2.
It's a that's here. Look, we have a different definition right now. I don't want to call it delta 1. Let's call it delta 1 tag. I don't care. I mean, this is just the detuning of laser 1 from the transition from 1 to 2. Laser 2 is on resonance, always. This one is sitting at. So this is the detuning of laser 1.
So what is the difference from before?
The difference from before was that we had a 1 photon detuning and 2 photon detuning. We were plotting everything from here. This was the drawing before.
Ah, okay.
So now this laser is on. Yossi, mute yourself. Okay, so if you think normally when you have a field and you scan its frequency and you shine it onto, then you hit a resonance, you'll see something like this.
It's like two states, like we did before the three.
You know, this is the probability. Yeah, that's the probability of ending up in state 2. And this is the frequency omega 1, 2. When the laser hits that frequency, we have maximum absorption. Now what will happen? At that point, there will be no absorption.
Because delta 1 is 0 and delta 2 is 0?
Exactly. We're on a dark state. So what we'll have is actually something that would look like this.
Rabbi, will they go through this state, this level? I mean,
Which?
the second one. I mean, the electron goes.
No, they don't.
But why? How can we know that it doesn't go from the first one to the second one and then immediately goes to the third one? So.
Oh, you can check the population here. It will be 0 as well. So that's a good, and I'll give you an intuitive explanation in a moment. So let's see. First of all, this laser is off. Okay, I didn't even turn it on. So population is here, and this laser is working very hard on empty states. Full gauge neutral. This laser is running, it's coupling those two levels strongly, does Rabi oscillations between nothing to nothing. And then I turn on this laser and I scan its frequency, and it's weak, does very little. And surprising enough, what we see is that, okay, normally I would say, well, I don't care about this laser. It does nothing. It operates on empty states. So why do I care about it? And I'm changing the frequency of this one, and when I hit resonance, instead of having maximum absorption, I have minimum. And ideally, none. And the absorption, so we see a split. So this is why it's called the, oh, sorry. I was mistaken twice. It's not that only that I forgot how to spell shallow. It's not shallow. It's Outler. This is the Outler-Towns splitting. Shallow-Towns is another one. Shallow-Towns is the Shallow-Towns formula for the line width of a laser. Towns is the same Towns. Outler is different. Sorry, and then the whole thing is broadcast to the world and recorded for infinity to know what a mistake I made. So, but in any case, the Outler-Towns splitting, not shallow. Well, but shallow did beautiful things anyway, so we could give him that as well. So now let me tell you what exactly happens here. Why is there? So of course this is an interference effect. This is a quantum interference effect that somehow nulls the absorption. Now let's think for a moment, what does it mean to have an absorption? Well, let's ask, I start with population here. What do I need to do in order to end up here? Well, one thing I can do is to just go up. So that's one possibility. I'll just jump up. How? By this laser. This laser will transfer me from here to there. And this laser is weak, so it cannot do much. I mean, it cannot Rabi flop. The Rabi flops will be very slow until some Rabi happens. So this is very weak. You can even think about this perturbatively. I have some probability of going up. But this guy is strong, so I can go up once. But I can go up, and then very quickly go down to state number 3 and go back up. So this is option 1, but I could also do a Rabi flop here. Now, this omega 2 is large. So having a Rabi flop here is fast. So those two possibilities, just going up or going up and Rabi flopping on the other leg, are indistinguishable. And of course you could do more than one Rabi flop. You can do twice and 3 times and so on. And basically all of them are indistinguishable. But do you remember something about a Rabi flop? What a Rabi flop is like doing nothing. Meaning if I do a Rabi flop, I start from downstairs, I go all around the block and go back. But if you remember, there's a phase coming with that. And this phase is not 0 and not 2 pi. It's pi. When you do one Rabi flop, you go back. Everything goes back to itself, except that you acquire a phase of minus. We have a minus sign. So normally we don't care. The population didn't change. The population started here and ended up here. But now we do. Because if you go up, you come here with some amplitude. But if you go up and do a Rabi flop, you come here with that same amplitude but with a minus sign. This Rabi flop on the other leg gives you a minus sign. So, and now there is a quantum interference between those two possibilities to end up here, which is just go directly or go directly and do a Rabi flop. And the Rabi flop is a minus sign, so those two interfere destructively. And therefore the process does not happen. Now this does require those two to be indistinguishable. And they are indistinguishable only when you are on to photon resonance. Only when indeed the energy, the frequency of this laser equals exactly the frequency of this laser, and therefore the possibility of just absorbing once from this laser or absorbing from this laser, emitting to this laser and absorbing again from this laser, all of those have the same energy. Only when all of those situations have exactly the same total energy in the end, then it is indeed indistinguishable, and then indeed they interfere destructively. But if you have a detuning here, then you could see it in two ways. One, you could say, then V0 is no longer dark, this 0 is no longer 0, and you have some probability of ending up in the excited state. This is one mathematical way of saying that. Calculate what V0 is and what the eigenenergy is in that case, and it's not 0, and the state does contain something here. So that's one way, mathematical way to see this. Or you could say, in the language of quantum interference, you could say, we have the situation becomes distinguishable because the energy of this guy and the energy of this and that, they don't end up the same, or you don't hit the excited state. Okay. So, that is the Eitler-Towns splitting. And surprisingly, right now we analyzed it in the case when this guy is sufficiently large. This one's weak. But the question now becomes, okay, so how weak does it have to be? Or sorry, how strong does this one have to be? What happens when the two frequencies are, for example, of the same order? Even if both of them are weak. Surprising enough, this destructive interference is very robust. It's always there. It's just that this splitting has the width of omega 2.
Because it takes time for the electron to do a full circle?
Right. That's the time. Now, so that means that when omega 2 is large, it does it very quickly, and the splitting they can become very large. Now, when omega 2 is small, then this window can become very narrow, but it doesn't disappear. Well, eventually it will disappear, but and then, so that means that you could have a very narrow window of transparency within the absorption line. So just in the middle of the absorption line, there sits a window of transparency. Now, okay, and then if you remember, what? You're asking if this goes up? If this... well, it depends on how strong this second laser is. If this second laser is very strong, then you really have a true splitting. This line splits into two lines, and there's a dead zone in between. And when you reduce this omega 2, then they become closer and closer, and eventually they almost sit within this, just this line. And then you can end up, when both of them are rather weak, you can even end up with lines that look like this. Really, it follows the same thing, and then here it will have some dip. Now, and the point is that this dip can be very, very narrow. Now, you have a very, very narrow feature. And then that means, I don't know, if you remember Kramer-Kronig's relation, there is a relation between the amplitude and the phase. There is a relation between the real part and the imaginary part of a Fourier transform of a signal. There is a relation between the absorption and the index of refraction. I'm not going to explain this deeply, but if you want to understand this more, then ask me later. But that means that inherently means that if you have such a change in absorption, it must come with a change of phase. If you remember, we mentioned at least once that when you drive a harmonic oscillator, if you drive it below resonance, then it doesn't absorb, but it responds in phase with you. When you drive it above resonance, it doesn't respond, or it doesn't absorb, but it responds with a pi phase relative to you. And when you drive it exactly on resonance, then it responds, it absorbs strongly, and it responds with a pi over 2 phase. Now this phase is standard. It's always there. So where there is absorption, the phase is pi over 2. Where there's no absorption, the phase would be either 0 or pi. So if I try to think about the absorption that was there before, so let's start with the simple case. The simple case says that I have an absorption line. Looks maybe like this. This is omega atom. If I ask myself what the phase is, then I'll see a phase, and the phase immediately relates to the index of refraction. I'll see a phase that does something like this. Well, basically here it will be 0, and here it will be pi over 2. Here it will be pi. So that's what the phase does. Intensity and phase of the response. Now that's pi. But now what happened to our line? It got split. So that means now we have two lines that are very, very close. So the absorption looks like this. And the point is that now this thing happens in a way twice. So we'll see a phase that maybe goes here like this and then goes here. And then here there will be some very strong reaction, and then it will go up again and eventually end up at pi. There's a very strong, so in that line there is a very strong, I'm not explaining it too well, but the phase response here induces a very strong slope of the phase as a function of frequency. And a very strong slope of the phase as a function of frequency means a very strong change in the group velocity relative to the phase velocity. If you remember, V, the phase velocity is omega over k, or in other words, in vacuum, this is just c divided by the index of refraction. The group velocity is the derivative of that. So it's the omega to dk. Now if we remind ourselves what is the frequency, omega equals ck, but then we have c over n k. And this n depends on frequency now. This is where the phase comes from. Now, so d omega to dk is actually just c over n plus c minus, of course, c over n squared times k dn to dk. And ck is ck, or I can write it in another way. There will be here omega. Omega is ck divided by n. So we have here omega divided by n, and that's it. dn to dk. Now, so those two are, if normally the index of refraction, the dispersion of the index of refraction, dn to dk or dn to the omega, just at the same time, this is a slow thing. So this contribution is small compared to that one, and the group velocity is very close to the phase velocity. The differences are small. But here we have a situation where there's a very strong slope. This term can become large. This is large in our case. And the contribution of this to the group velocity can become very large. And in fact, if this is very strong, maybe this one will even cancel that one. Maybe the group velocity will become negative. What does that mean? It actually means that you have the phase moving forward and a pulse form actually moving backwards. But so you could have all kinds of crazy situations. By the way, it can be faster than the speed of light, because nobody told you what this sign is going to be. There's a minus sign here, but who said that this is positive? Maybe that's negative. Maybe this group velocity can be faster than light. So all those options exist. There is what we call fast light, when this group velocity appears to be superluminal, faster than the speed of light in vacuum. And then people start asking crazy things. What does that mean? Does this mean that the light exits before it enters? What does it... we can say something about that. And so all of this started this whole thing of slow light or fast light. And all of them has to do with situations where you play with this term by tricks of EIT. Using tricks of EIT, using these kinds of situations. Let me say something about, don't worry, Einstein still sleeps well. It's not really a problem. Why? Well, look. Maybe the group velocity can become very slow, for example, or even large. But then the question is, what do I need to do in order for this to become very slow or very large or change abruptly and strongly? We need a very strong slope here. But this slope is also related to the width. So that means that this effect is by definition narrow in frequency. You cannot, if you can ask yourself, well, what will happen if I throw in a short pulse? Well, if you throw in a short pulse, it will have a wide bandwidth, and it will cover not only this tiny window here, it will cover the entire blackboard. And then it will be distorted in some way, but it wouldn't appear to do anything that is very funny. What do we see? We can turn on the light very slowly. We have and then there are effects of the speed of the group velocity of some kind of a pulse appears to be moving very slow. But which pulse is it? It's a very, very long pulse. It's much longer than your sample. I have some atoms sitting here, and I have a pulse of light that looks like this. And it's coming slowly through the atoms. And it appears to be moving slow or fast through the atoms. But most of the time it moves in vacuum. It's never entirely in the medium. because it's a very long pulse, compared to a medium that I cannot make a medium interacting with lasers that is a kilometer long. And I will have kilometer long pulses. So that's a practical answer why those things are not a problem. And then the other, there's also an important thing, that is, which is the velocity that cannot be larger than the speed of light? Again, a misconception. People told you, aha, well, the phase velocity, it can be larger than the speed of light, but the group velocity cannot. Have you heard that more than once? Wrong. The group velocity can definitely be larger than the speed of light. But is there any information moving at the group velocity? Now let's answer for a moment, what is really, when we want to say something about information, what is the information? There was no light and now there is. This is information. Somebody turned on a pulse over there. I want to know when I'll know it. What do I need to know? The omega 2 decay? I don't know. The omega 2 decay is the speed at which the peak of the pulse is moving. If you have a pulse that is sufficiently narrow, its peak will move at that frequency. But the peak velocity, does this reflect information speed? I don't know. Maybe this pulse is going completely distorted when it moves through that medium, and this peak can appear to be moving fast or to be moving very slow. I don't know. It is interacting with atoms. We have a very strong light-matter interaction. What is information? Information is there was no light and now there is. That is called the leading edge velocity. Meaning the very first, if there is some light, well, this is not as a function of time here, but there was no light and now there is. The question is, how fast does this propagate through the medium? And this one is the one that is never, ever more than speed of light. Okay, I was talking far too much, and we wasted an hour and a half on something that should have taken less than an hour, which means that I enjoy what I'm talking about. So let's take a 10 minutes break and then continue for something like 45 minutes to discuss to discuss coherence, classical coherence, leave this stuff of three-level systems, and I hope you liked it. And yeah, new chapter in 10 minutes. We'll start at 5:45.
אבי, אפשר שאלה?
Sure.
לא בדיוק הבנתי מה היחס בין ה-outlet הזה, ספלינג, לבין מה שעשינו לפני כן עם ה-dark space. זה לא אותו דבר, זה לא אותו מצב שכאילו ממש קריקה, או שזה בדיוק אותו דבר?
I'll answer in a moment, but this may be an important call, so I'm sorry. Hello? Wasn't that important after all. So it actually is related. Well, the point is that the relation is the following. When this laser is weak, then on resonance, this is a dark state. So on resonance, surprisingly, exactly on resonance is the situation where it does not interact with the light. Do you understand what I'm saying?
כן, אמרנו שזה שהאומגה אחד חזק, דווקא הוא רמה אחת ריקה. זה נמצא ברמה 3.
No, no. Now, all population is here. Omega 1 is weak. Population sits here, and you ask yourself, so you have the laser, population is sitting here, and omega 1 now is weak, so it almost doesn't disturb it. It has some small probability of taking it out. And we ask ourselves, what is that probability? What is that probability? Where will it take it out to? It will take it out here. So we ask ourselves, this is what we draw. What is P2? What's the probability of finding an atom in the excited state?
אבל לא אמרנו שזה 0 במצב של ה-V0 הזה?
Indeed, that's what happens here. When you are...
זה על אותו בסיס שכאילו אנחנו מדברים על V0 ששם אין אטומים ברמה 2?
נכון. Well, exactly, that's the point. When this laser is on resonance, meaning when this delta equals 0, that means that we hit the 2-photon resonance condition and that this state becomes then dark. It stops interacting with the light and the absorption disappears. This is exactly what happens. You start getting, you turn on this laser and you start scanning its frequency. Originally you see, well, yeah, I'm hitting the absorption line. I see more and more population going on to the excited state. But then when you're exactly on resonance, the absorption disappears because you hit the dark state.
אוקיי, זה מה שאמרנו כאילו שבשתיים לא נמצא, ועכשיו פתאום הכל בשלוש.
לא, nothing is in 3. The dark state was and stays 1. Remember, the dark state has to do, tell me what is, this one is weak, this one is large. So the dark state is always state 1.
נשארנו בזה שכאילו אומגה 2 גדול עדיין.
הגברנו
את אומגה 1, אבל הוא...
No, I didn't think, לא הגברתי את אומגה 1. I didn't increase the intensity. I'm scanning the frequency. I'm scanning I'm scanning through the absorption line. I'm not talking about the Rabi frequency. The Rabi frequency is small, remains small. It's always small. The situation in stirrup is when we change the relative intensity. The detunings stay constant, but the relative intensities change. And then we transfer population from one state to the other. Now we're doing something else. The intensities are constant. This intensity is large and constant. This intensity is weak and constant. But I'm changing its frequency. I'm scanning across the absorption line.
אוקיי, סבבה, תודה.
שזה נחשב מאתגר, כי בסוף זה אומר...
כן,
זאת אומרת... 2 להיות דווקא קטן.
לא, אתה צריך, אבל אתה צריך, העניין הוא אוקיי. There's one thing that we didn't talk about here. What's the challenge? For example, what happens with broadenings? Specifically when you have an inhomogeneous broadening. Now, the point is that you have an inhomogeneous broadening. That means that different atoms have a different absorption line. For example, they have a little bit of a Doppler. So in a thermal cloud, you can never see this strong effect. Because in the thermal clouds, the detuning of different atoms is different, and those atoms that are now exactly splitting are only a small part of the entire cloud, and you see nothing.
But if you take some atoms and I freeze them?
Oh, well, how do you freeze an atom?
Yeah, you can.
Okay, so you need cold atoms. So this is something that when people could cool atoms to practically the ground state, and they could have a BC of atoms which are practically standing still, then they could do these experiments when they had a very narrow line and they opened a very narrow EIT gap in it, and then they could have a very strong slope but still have an effect. I mean, that doesn't disappear, it doesn't smear out. You could see a very narrow EIT feature and still see it, and then you could reach situations where the group velocity came down to running speed. So, okay. So, is it time? Yes. So, new subject. We're going to talk about, we're going to go back to the light and discuss coherence. Our plan today is to describe first order coherence, second order coherence, and the Hanbury, Brown, and Twiss experiment. Hanbury, Brown, and Twiss experiment is an experiment that was done in the 50s. It was completely classical. It still is completely classical. And it was the way to see that even very, very respected physicists can make very, very stupid mistakes. We'll discuss. So we want to talk about classical coherence of light. Now, when we talk about coherence, is actually, we want to talk, well, many times so far, we discussed the field. We said, you know, the field of the laser is a function at point specific in time. It has some amplitude, and it is this, I don't know. Yeah. Maybe I plus complex conjugate. I wrote this. That was a specific point in time and space, and well, maybe I could write R, and then there will be some A, which depends, of course. And then we can write, we know, I mean, this is a Fourier kind of thing, so maybe there's a sum over K vectors, and here we have A K times e to the I minus I omega t minus K dot R, and you know all this, plus the complex conjugate. I can write this. And this tells me also how this thing, which is at some point in time something. So this was at a specific frequency, and maybe there are many frequencies. And of course, there is a relation between K and omega. So yeah, omega equals C times absolute value of K. So omega, for every K, there is the omega of that K. But, okay, so I can write this. But the question is, what do I need to know in order to know the field? I want to write, I want to know the field. I want to measure it. Know what the field is. I need to know A, at least one of them. Well, I need to know all the A's if I want to talk about the field. But let's talk about right now a single frequency even. So if it's a single frequency, I need to know A, but A is a complex number. So I need to know its amplitude and phase. How do I know it? Is there any way to measure a phase? The answer is no. I mean, when we are in radio frequency, then the electric field or the voltage it may be time dependent, but it's slow. You know, if I want to measure the field, I'll put in maybe a capacitor. I'll let the capacitor charge, and I'll measure the charge on the two. And I'll know E. If E is static, of course I can do this. If E is changing slow enough, of course I still can do this. The capacitor will tell me what the field is within that capacitor. But when the field is changing too fast, then the electrons are not fast enough to respond. So, or in other words, we don't have detectors that are small enough and fast enough to actually follow the field. What we measure is intensity. We can't measure this. What we measure is the intensity. And that, so to know the field, coherence is about knowledge. Meaning that I can say that a laser is coherent. It means something that I know about it. I somehow know its field better. But does that mean that I know the laser phase? No, I never. So what can we measure from an optical field? The answer is we can measure the intensity, not the phase. Even more so, we can measure intensity, which is the absolute values squared of the field, or just A. I don't know the phase. And to be honest, I can't even measure that. At least not truly instantaneously. Every detector has some integration time. The detector, actually, what we can measure is only the average value of this. What we can measure is this. The truly measured quantities is I average, which depends on the time of measurement, but also on the integration time tau, which is a property of the detector. How long does the detector, and it's basically this. Let's say it actually we can say that what we can measure is an average over the if you shine an extremely short pulse on a detector, what will the detector show you? Meaning, suppose that I have a detector here, and I'm looking at what do I see? I look at the photocurrent. Now there's a problem. We mark intensity as I, and we mark current as I. Well, yeah, we can do that. So that would be little I of t. It is proportional to E of t squared. This is what we usually think about. That's what a detector gives us. It tells us what's the intensity of the light that's hitting it. Yeah, but let's suppose that if I have here a constant intensity of light, then indeed I'll have a constant intensity of current. If here I have a pulse that is rather slow, then the current here will go up and down. But if the pulse here is like a delta function, extremely short, then here there will be a pulse of electrons, but it will not be as short as this. It would look like something that is longer. What?
Like a rect function.
I don't know if it's going to be a rect function, but it will be it will show some, it will have some integrator response. Meaning you, for example, the light comes in, and indeed it emits some photoelectrons. But those photoelectrons, they take time from all kinds of... And if I'll give you two pulses that are very close to one another, your detector will not be able to tell them apart, because they would be 1 and 2, and who can tell that it's not just a single pulse? And this has to do with the fact that what we're measuring is the average intensity over some window, which starts from, say, t up to t plus tau. Now, of course, it's not exact. I mean, this is assuming that I have a perfect integration time, that it starts integrating and ends. Now, in reality, there is some response over some average response time tau. But in any case, so this is the only thing I can measure. What I can measure is the average intensity over the response time of the detector. So, and I'm obviously losing. Well, what do I lose? First, if there's very fast changes of the intensity, I obviously lose them. But there's something that's even more important, and that is, even if there aren't, I have no way of measuring the phase. There's no way I can know what the phase of the field is. An optical field, we can't see the phase. So what do we do about the phase? And fast variations are a problem. But, you know, if fast variations are a problem to me, well, maybe I can get a faster detector. You know, the detectors got better over the years. And you can have today detectors that respond as fast as 10 picoseconds. So maybe that's fast enough. I mean, maybe you can follow the fast variations. Tell me if 10 picoseconds is sufficiently fast or not. We can make pulses that are even shorter than this. But that's not the point. The main point is that the phase, it doesn't matter how slow the light is changing. There's no way of measuring this. At least not directly from photodetection. So what can we do? What do we do in order to see something that relates to the phase? And that is interference. And the point is that interference always involves two fields. We always measure the intensity. But we measure the intensity of two fields that interfere. So, of course, if we have two fields, E1 plus E2, and we take the intensity of that, then that always, well, you know what this is. This is E1 squared plus E2 squared plus twice the real part of E1, E2 star. Or I can write it as, you know, E1, E2 star plus E1 star E2. Or, in other words, if this, now assuming that we have, supposing now that we have here, this one is A1, A2, e to the I, sorry, A2 star, e to the I omega 1 minus omega 2. Now then, of course, now here plus Well, I don't want to write it again. Plus complex conjugate. Now, if the two frequencies are the same, so that's general. This is the term, this is what happens here. If those, so then we took two fields. Now in a moment we're going to interfere the field with itself. So their frequency is going to be the same. But conceptually, obviously, when the two fields, when omega 1 equals omega 2, same frequency, then what we have here is A1, A2 star, real part of, and that depends on the relative phase only. So that means that A1, A2 times e to the I phase 1 minus phase 2. And that, of course, the real part of this, or you could say that it is just what you have here, is the amplitude multiplication times the cosine of the relative phase. That is just A1, A2. So I could even write it in a different way. This part of the interference goes like square root of I1, the intensity of 1, times the intensity of laser 2, times cosine of phase 1 minus phase 2. So that means that what we can measure, so indeed we can see things that relate to phase, but which phase? Only the relative phase between two lasers. So if we do interference, gives us the phase difference. But it's only the difference. I don't know the phase. I only the phase difference. So a phase is always defined only relative to something. And of course, the absolute phase is something that not just we cannot measure, but also doesn't mean anything, because all that it means is when is the time, when did the clock start? And we can start the clock whenever we want. So we cannot measure the absolute phase, and even if we could, it doesn't really tell us anything. So now, but I want to now say how good is a laser. You know, I have a laser, is it good or bad? You know, is this lamp, is it coherent or incoherent? I want to say something that, so I cannot say, it's like asking how well can I know the phase and the amplitude of the field? Well, the question about the phase is irrelevant. I can never know the phase. But I can ask how stable is the phase. So if I want to have, for example, a laser, I can ask myself, well, how so coherence means, as I said, knowledge. So that equals. Of what? No. There's a W here that should be. Knowledge of what? Of the of phase, well, specifically, so primarily of the phase, and specifically of its stability. How stable is the phase? If I know the phase now, Okay? So I can, you know, I can write this.
It's the relative phase.
Yes. Relative phase to a specific point in time. So I'll tell you in a moment an experiment. You know what? Let's do that. Exactly. I want to ask myself, is this phase stable? How do I check? So I'll do the following. I have a laser. This is E of t. I don't know what it is. So I can write E of t equals A of t amplitude times e to the I phi of t times the carrier. I can always do this. I mean, this is just a mathematical point. And now we can ask ourselves, okay, is this just constant function? Is it just a constant number? Or does it change? Now I'll do this. Okay, I'll take this laser and split it. And then here I'll have some, and then I'll have it meet with itself. So here, this is a beam splitter. Now we're talking classically, we're not saying anything about any photon. But here, so here I have 1 over square root of 2 times E. And here there's 1 over square root of 2 times E of t. The same. But now when we come to here, this one came through. Let's consider this distance as 0. Okay? Of course, let's consider for now that those two beam splitters are very close, but that doesn't matter. The important thing is the relative delay between the long leg and the short leg. Okay? So here what I have is 1 over 2. There's of course a part that goes out to this side, but I don't look at it. I'm just looking here. So what we have here is half E of t plus E of t plus tau. So this is just, what I'm doing here is I'm building an interferometer which is unbalanced. So here there is a delay tau. And I can ask, okay, what will this show me? Well, now what I'm going to do is I'm going to put a detector here. I'm going to measure this intensity. So if I measure that intensity, what will I see? So I will be what? It will be, well, of course, there will be I of t plus I of t plus tau plus square root of I of t I of t plus tau times what? Cosine phi of t minus phi of t plus tau. Same thing as we did before. If I look at this term, what's written here? What is written here is basically the real part of E of t times E star of t plus tau. Sorry, maybe I shouldn't have used tau here because we had tau for the integration time.
We can separate them.
Yeah, I know that you can separate, but I want to use both in a moment. So let's call this one here the integration time. Let's call it bigger t. Big T. Okay? So now, as I told you before, what do we really measure? Well, honestly, I don't measure this instantaneously. I measure this averaged over the integration time of the detector. So now, the question is, okay, so now C. The question is, this interference term depends on what? on the relative phase between the laser now and the laser in tau time delay. If the laser is a really good laser, meaning if this phase does not change, constant, hopefully also this amplitude doesn't change. But as I told you, the amplitude is the smaller problem. If this phase is constant, then the independent of what this tau going to be, I'll see interference. This laser will interfere. I'll see this thing will be constant. And this cosine will be something. And it will not depend on time, because the phase difference is constant. It depends only on the delay. What will we see? We'll see, well, up and down and up and down and up and down. At what? Well, I should have been here. I should have wrote, okay. If I wanted to do this correctly, I was too fast. I'm sorry. There's the phase difference, of course. Phase of t minus phase of t plus tau minus omega 0 tau. Of course, you can see here, this is what I should have written. So you can see that now at time t, there's the variations of the relative phase, and then there's the absolute phase that carries on normally. And then what will happen? We will have this laser at time t plus tau. So the phase will be that of the later time, and there will be the acquisition of this constant carrier phase. And so now basically this, if I do an experiment, then what do I expect to see? You know, the measured intensity here as a function of the relative delay. Then, if the delay is small, this phase difference is 0. Now this is running very fast because this is running at the carrier frequency. So we're going to see, you know, at exactly 0 delay, we'll have constructive interference, and then it will become destructive, and then it will become constructive again and destructive again. But if we keep on going at larger and larger delay, then these fringes, they slowly disappear and we get nothing. Just this term. I'm talking about only this term. Forget about these two guys. Okay? This is just the oscillation interfering term. Why is it? Why did the fringes disappear? What is this time over which the fringes disappear? First of all, it is called the coherence time. And what is it? It's exactly the time over which this phase is no longer stable. This laser, if this was a true, pure cosine, single frequency laser, then this A is just a number. And those fringes appear to infinity. Because whatever is written here is phase minus itself, so this is nothing. But in a real life, then the phase of the laser, I don't know, it slowly varies. It's not constant. By the way, we can talk about what's the phase of this lamp. Well, this one is varying very fast. But so, how long are those fringes? This time, this average time, is called the coherence time, tau c. And if we're at it right now, let's make a correct connection between this coherence time and the bandwidth of the light. So now we're going to learn the Wiener Kimchi theorem. So today is the lesson or the lecture where I break my teeth over people's name that I don't remember. So let's see. So now, as I told you, what do we measure? So I told you we measure this. But no, we don't measure this. We measure this averaged over time. Right? What do I actually measure? I'm putting here a detector, and this detector has some integration time. So now, if this thing is sufficiently stable over the integration time of the detector, I'll see it. And if it fluctuates faster than the detection time of the integration time of the detector, then I won't see it. Why? Because I have plus cosine and minus cosine, and the fringes, it's like saying those fringes are running left and right. Sometimes I'm sitting here at time delay tau, but the phase is not stable. So sometimes it's destructive, sometimes it's constructive. And on average, I have, well, now it depends. If I am fast, tell me how fast I am in order to detect this. And maybe sometimes, and if I'm too slow, then I'll see nothing eventually. The question is, so what we can detect is this. 1 over t detector, that's the detection time, times the integral of what? From t up to t plus t detection this is this term. What do I have here? E of t times E star of t plus tau dt. Now, so this is, I can give it a name, I can define it. This is what we measure. This is what the detector shows me. Now, so first of all, let's take two interesting cases. So now, let's assume that the detector time is long, very long. Okay? So I assume a slow detector. If it's a slow detector, so I can even say that this goes to the integral from minus infinity to plus infinity . What is this? Has a name. Autocorrelation. This is the autocorrelation of the field with itself, with separation tau. So what is the Fourier transform? And this is what we call the coherence function. So this is the, we'll call it the coherence function. People try to use many times, mentioned with gamma 1, and it's a function of tau. Okay, we'll define more carefully. So this is gamma 1, that's the coherence function. This one depends on both t and tau, and honestly also on t detector. But if we assume that t detector goes to infinity, then gamma 1, which depends on t and tau and t detector, under this case stops It doesn't depend on time anymore because we integrate over an extremely long time. And so this goes as T detector goes to infinity to being gamma 1 of just tau. And that is the autocorrelation of the field. Hard to see, I think, because, well, and that means that if we want to say, so now we have an immediate relation of this to frequency, because what is the Fourier transform of the autocorrelation? It's the spectrum, the intensity. So that means that if I do a Fourier transform, that means that gamma 1 of frequency omega equals this is, or you know what, let's even write it like this. So now gamma 1 of tau, how does it look? Well, gamma 1 of tau looks like, I don't know, it has some envelope. It's a cosine oscillating and it's dying, and it has an envelope. So this is how, this is tau, and this is how gamma 1 looks like in tau. That means that what you see here is directly the Fourier transform of the field, the intensity. So what it tells you is this. When you do a Fourier transform, if this is the atomic area, if you have here a width, and that is, I'm doing a Fourier transform, but this is just nothing but the intensity squared. That means, for example, that this coherence time tau is exactly 1 over the spectral width of your source. If you have a laser that is extremely narrow in frequency, that by definition means that its phase is very, very stable. It has a frequency that you almost perfectly know. So that means that if you know its phase now, you'll keep knowing it for a while, as long as its frequency is indeed not changing. And then after some time, maybe because you estimated the frequency wrong, then you don't understand exactly how it accumulates phase, and then you lose track. So this is what this thing tells me. How far can I go without losing track of the phase? And what it tells you is, tell me what is the frequency. If you know the frequency very well, meaning if this delta omega, what's the spectral width of your source? This is not just, it's exactly 1 over tau coherence, 2 pi, but you know, we wrote like this, so we'll write 2 pi. So by the way, if you want to know how narrow band, okay, so now I can tell you the following. I can take this lamp and I can put it through an interferometer and measure its coherence length. It will be extremely short. Why? Because its phase is running up and down like crazy. Its frequency is terribly defined. It has its frequency is, you know, this is Suppose that it's a white source that actually has a very broad spectrum. And then indeed, if we do something like this experiment with this lamp, we will see fringes only when the delay is practically zero. Once we open up some delay between the two legs, very quickly the relative phase becomes unknown. Why? Because this lamp does not acquire phase in a deterministic manner, or not even close to deterministic. My knowledge of its phase is terrible. But if I have a really, really good laser that has a very, very clean frequency, it doesn't change. Well, then I can do this by taking a spectrometer and measuring its line width and see that it's extremely narrow. We'll talk about this in a moment. What does it mean? It means that if I'll do this kind of experiment, meaning I'll take that and I'll measure the relative phase, then I'll be able to see fringes for a very long time. I can take a good laser and make here a delay of 1 meter and still see good interference. What does it mean? It means that the field, and the field with itself after 1 meter, 1 meter is about 3 nanoseconds. So the field now and the field in 3 nanoseconds, they are still, the relative phase between them is stable. Or in terms of delay, so that means that the phase over 3 nanoseconds, it really behaves like a nice sine wave. And then, so, okay, 1 meter coherence length or 3 nanoseconds coherent time is not bad, but you can definitely have much better. You can have a laser that is much narrower than this. So meaning, suppose that I have a laser that I know that is 1 megahertz wide. So its line width is only 1 megahertz. It has a very good optical frequency, and it is narrow, only 1 megahertz around that line width. Well, that means that its coherence time, by definition, is going to be at least 1 microsecond. Actually, if it is exactly 1 megahertz wide, then it's going to be exactly 1 microsecond long. 1 microsecond is quite a long distance. I mean, you can make a very long delay. If I told you 1 nanosecond, it's good to remember. 1 nanosecond is 30 centimeters, or 1 nanosecond is 1 foot. If you remember that 1 foot is approximately 30 centimeters, then a nano is a foot, and therefore a microsecond is 1,000 feet or 300 meters. So 300 meters is rather long, and you could have a laser that's also a kilohertz line width. That becomes already quite a long distance. That will be very hard to make this experiment to actually measure its coherence time through a long delay. You'll need a very long fiber in order to do that, probably, because it's hard to fit that in the lab. And today we can have even lasers that are a hertz line narrow. So meaning that they have a very good frequency down to a single hertz. That means that their coherence time is 300,000 kilometers, or the distance to the moon and back. This kind of a laser, you can send it to the moon and back, and it will interfere with itself, with its copy that is still here on the ground. These are experiments that have been done because the Americans, when they landed on the moon, one of the important things that they did there, except from collecting some stones, was to leave a retroreflector on the moon, which reflects light back. So these are measurements that have been done. And if you have a sufficiently good laser, you'll be able to do that. And then you can even measure the distance to the moon, or at least how it changes slowly, by measuring the stability of this interference. And maybe if this phase is changing over time, it's something you can measure. Now, okay.
I have a question.
Yes.
Are those lasers typically CW or pulse?
Well, you can discuss both, but for now we discussed CW.
Okay. Thank you.
So far, okay, so I think, so what I told you now, so now we need to start defining things mathematically. So we're going to say, okay, I can define the first order coherence function. This first order coherence function depends on time t, on relative time tau, and that is, and now it's a definition. This is the average of E of t times E star of t plus. Now, I wrote here some average, and this is actually a little bit different. This is an ensemble average. So this is, so now we have the definition of the first order coherence time, of coherence function. And which is the first. Of course, there's going to be more, but the rest will be next week because at some point we need to stop. So this is some average. Now, so far we understood what this average is. This, please, whoever is not muted, please be mute. So far we understood what this average is. That was the averaging time of the detector. But now I want to define it a little bit differently because I want to say, look, this is an ensemble average. Ensemble over what? Over all the possible instances of this field E. Why? Because maybe I'm doing this, I have a source, I don't know what this lamp is going to do. I turn it on once and then I turn it on again and then I turn it on again. Every time it does something a little bit different. So this is a definition, and this is an ensemble average. And then ensemble, and I'm going to leave it loosely defined. And usually, so in the experiment, this is obvious. This is the time, the integration time of the detector. Okay, so now, and this is, and look, this is something that captures exactly what we are looking for. What is, if I know the field at time t, will I know it later? In order for this to be non-zero, you need first the intensity to be relatively stable, and the phase, and that's the most important part, you need the relative phase to be stable. This is a complex number. And this complex number tells you what is the average value of the intensity multiplied by e to the I, by the average of the e to the I phi. And if this, so yeah, that's the complex degree of coherence. What we can measure, by the way, as you saw already, we can measure the real part of it. What we measure is the real part of gamma. But that's okay. I mean, we can also measure the imaginary part of gamma. All we need to do is to put an I phase. So we can measure gamma experimentally. And indeed, that means that basically, and theoretically we define it as some ensemble average. Okay, so this is going to be our starting point next week, because now is time to stop. And then, so we'll take this definition, and then we can see that, for example, I can do the same over space. So I can talk about, this is temporal coherence. I have a source. I'm asking what's the relation of this source from now to later. I can also ask the same question in space. If I know the field here at one time, do I know the field here at the same time? So with the separation of distance between them. For example, if it's a perfect plane wave source, then the answer is yes. Or even if it's a spherical wave, then the answer is yes. Because it's a perfect spherical wave. So if you know the phase here, you know it everywhere along the front, the phase front of your laser. But maybe it's a lamp like this, which is terrible. And there is no clear relation between the phase on that side of the lamp to the other side of the lamp. So then there is we don't know. If I know the field here, I don't know it there. So this is spatial coherence. This fact that we can discuss, okay, if I tell you what the field here, how well do you know what's the correlation of the field here to the field somewhere else in time or in space or in both? This is the definition of coherence. It tells you, well, how well do you know your source? Is it stable in time? Is it stable in space? Now this is the definition of first order coherence, and then we can start playing things of higher order, meaning put here E squared, put here maybe intensity. You can ask, what is the stability of all kinds of other quantities as well? And then it will be. So that's going to be our discussion next week. Next week is mathematical coherence and Henry Brown and Twist's experiment and semi-classical photodetection. All of those in 1 week, and later we quantize the field. See you next time.